In the second problem of the homework, there was sort of an essential thing that I wanted you to notice, that if we produce, I could have said it on Monday, this right-handed guy, N, we had to find a way of producing it. Remember, and I said we did a new theory. In the standard model, we couldn't produce it. You remember, we simply couldn't produce it in the seesaw picture. The seesaw picture was done by assuming that M transpose was much less than Mn. And the theta, the mixing angle between N and whatever state it will mix with the neutrino, is given by M Dirac, right? It was, I think, Mn minus 1 the order times M Dirac. Or the other way around, it's not so important. So you see, we said the production then will be, the production will be proportional to theta squared, but this from the seesaw formula, which is M Dirac 1 over Mn M Dirac, and there is a transpose, roughly, is of order M nu over Mn. So obviously in the seesaw picture, this is an extremely tiny number we are never going to produce. This we didn't like. I claim I have an answer why neutrino is light by having a new particle that I cannot produce. Okay, that's not very, that's more metaphysics or whatever. I'm not fair maybe to the semantics of metaphysics. We also didn't like the fact that I couldn't predict this M Dirac. So it turned out in the homework, we said if there's a new gauge boson, imagine that there is, and we produce it. And most of you noticed from what I said or what we commented before, then N would have two channels. There is this remarkable thing of Majorana. See, because the issue from the very day that Majorana came up with this incredible thing is, how would you and I know for sure that the particle is Majorana? See, neutrino's double beta decay doesn't really look inside the particle. You just see that there is a process that behaves as if the guy is Majorana. It could be something else that causes it. We said it could be new physics. So here the point is that if I have a Majorana particle N that I can produce at the collider, then N will produce, and this is what is nice, half time into an electron or whoever, and half time into an anti-state, okay? And so you would actually see, we said we had two things which we liked. Just like the neutrino is double beta decay, there was an analogy that we would produce two same sign leptons, right? Complete analogy. Same diagram, we took the same diagram, we did a rotation in the plane. And we came up with that. So there was E plus W plus, or E plus pi W minus. 50% of the time. So see, this is what would be really beautiful about producing this guy. We could check, we would know for sure. Not only we would see lepton number violation as in this process, but we do actually see and know for sure that the guy is a Majorana particle. All we have to do is identify charges, which is done. We've done. And then we said that how will the guy decay? I sort of stopped there. We're going to go and talk about the Higgs today, but I think the high time is that we do something that we will do today. We said that N will decay into, say, an electron plus an up quark. We found the three, maybe this is better. Yes. Right, let's conserve charge. So we said then we produce these guys in a three-body decay, you computed that. And that, I said, becomes a jet. There are no free quarks in this world. They hadronize, they have strong interactions, they become jets. So why do I say that? I mean, this is a sort of strange thing that I say. How do I recognize this? Why do they go as jets? After all, quarks have these strong interactions that keep them together to make this funny object that we are. Protons and neutrons that give nuclei and the world as it is, okay. So how come I go through this strange language of talking of quarks as if they are free, and then I say, well, there are no quarks, they're just jets, you know, I do this funny thing, okay. Which is sort of a high time maybe then to speak of how we, and what we know about the strong interactions that allow me to do, being sometimes cavalier, but not to be wrong, maybe not to be very precise. Okay. So we are going to talk about strong interaction. Which is usual when I want to show you how the actual development took place, take me back to history. But actually history may be useful here because the history may be what more or less you know, I think, okay? Unless some of you know more, then you should, it should be good. But first, why do I say that, where should we start? Many times we made the statement that quarks carry color. How do you and I know that? So let's start with basics, okay? Let's talk about QCD, the theory of color, the dynamical theory of color. And let's make some important historic statements, okay, which affects today that quarks carry color. They come in 3 different colors, okay? Why do I say that? Give me some evidence that has been accumulating that actually you know. You yourself have been checking it. You're an expert on this.
Some decay.
Decays, yes. For example. For example.
Smirnov told us, but
no, you don't need Smirnov for this, or me. You know more than Smirnov.
No.
You've been doing it. Every homework had color. Almost everything you calculated had color. When you calculated the Z decay. When you calculate W decay into quarks, you always took the color, and you agreed with the PDG, with the experimental data. Without the color, you know, there will be a factor of 3 off, okay? So Z decay into QQ bar, W decays into, say, U bar D. Okay, you multiply every time by 3, actually the number of colors, quite suggestively 3. Some other process that you find, right? As I think, well, pion decay, for example. Pi 0 decays, it's made of quark, anti-quark. If you remember a pion going into 2 gamma, well, maybe you forgot that, or maybe you didn't study it very carefully, it doesn't matter. Another decay, but there are a bunch of decays. We did a top quark decaying into, what should I put here? Maybe plus. You counted, this was again color, and so on. But why was it introduced to start with? People didn't compute these things. There were no these things to start with. How did the color come about? That's what Smirnov told you.
There were hadrons with 3 quarks.
Why? Right, hadron. The idea, of course, okay, let's go back. So, quarks, the idea was the idea of bookkeeping, right? It was very nice that you have all these mesons and so on, and baryons, and you could describe all of them by 3, by having 3 quarks in the, in other words, quarks. So you can go less basic, okay, Gell-Mann and Zweig tell us they can do a great bookkeeping by saying that the baryon is QQQ and that the meson is QQ bar or Q bar Q. And it's sort of interesting, this is the only thing that we see. There's another thing that is emerging, you know, it's interesting. We don't see QQ states. We don't see, say, QQ bar states and so on. We see only these states. This is to comment in a moment, okay? Actually, these states are color singlets, okay, as you are. So why did I have to introduce color? Okay, there are three baryon is in proton. For example, proton is UD, neutron is UDD. There was a funny guy, baryon, which had double charge. So we made those 3 up quarks, so you remember. And it was in S0 orbitals, in S0 state, so it had a symmetric wave function. But it's a baryon and sort of didn't agree, it was hard to digest. And some of the ideas, okay, there was Wally Greenberg, who introduced some idea of parastatistics, okay, who was actually to become I was a postdoc at Maryland, Wally Greenberg, but more clearly, Nambu, and Nambu said, well, let's introduce a quantum number of color. Let's imagine that quarks carry another SU3 index, we'd say about. So that this particular combination would be antisymmetric and at the same time invariant. Why is it invariant? Remember, the quarks would transform as U. Quark would transform as U times Q. Now I'm talking of a single quark. This is not in the flavor space, right? So that means Q alpha goes into U alpha beta, Q beta. This is sort of a horizontal interaction. Take a quark. It's not up becoming down, it's up staying up. Okay. This is what a gluon does. Today it is whoever it is. But the transformation would be just among the quarks of the same charge. So this would go into U alpha alpha prime, U beta beta prime, U gamma gamma prime, U alpha prime, U beta prime, U gamma prime. This is now small u. I know epsilon alpha beta gamma. This will be transformation, right? This thing is okay. Please, if you forgot this, I invite you to check. This is epsilon alpha prime, beta prime, gamma prime, determinant u, u alpha prime, u beta prime, u gamma prime. So I choose a transformation that I now specify SU group, SU3, determinant 2 is equal to 1. Okay? So this combination is invariant. This is the famous way of getting invariance. In SU2, you always got this invariant by anti-symmetrizing the limb. You would take spin up and spin down. When there are 3 colors, you have to anti-symmetrize 3 times. This is already suggested that the symmetry is SU3. Well, it could have been maybe, you could say, why didn't they try to say that it is SO3? And these are triplets of SO3. Well, first objection, SO is real and these are complex fields. So it's a tricky thing to make a real transformation of complex fields. But can you tell me from what I've written here that it couldn't have been SO3? Okay, imagine whatever I do, I always said, will be minimal, okay? And this is how the fathers of great physics always did. They've chosen the minimal realization of whatever idea they had. So SO3 would be smaller than SU3. So imagine that the quarks, so I'm asking, could quark be a triplet of SO3? No, this would be invariant. Product of 2 vectors is invariant, not just vector and anti-vector. Obvious, there is no even distinction. So in other words, there will have to exist states like this, okay? And this is one of the crucial aspects of the theory of quark dynamics based on color, which is one of the essential facts of nature. There are no particles like this in nature. And SU3 theory, so no, answer is no. We need SU3 with a proviso that only SU3 color singlets are physical in terms, let me just keep physical, maybe the better, free states. for some reasons that we have to explain dynamically, the non-singlet guys are kind of confined inside these singlets. Right? If you have to imagine our singlets, mesons or baryons, like shopping bags that you have tightly closed, and it's full of stuff that can, move around, and often creating problems as you're walking, but they are nicely confined if the bag is tightly closed. Okay, so SU3 is the minimal realization of this that gives us, and apparently correct. And then, as we said, the evidence kept accumulating with great precision. But there was a frustration. There was a deep frustration with strong interactions. What does it mean then to talk of quarks if they are confined inside you have strong interaction that doesn't let them go out. So what's the sense of talking that I can never look into this bag? That's different from the shopping bag that we nicely then open at home and check the ingredients. And this was the 60s, okay, as this puzzle was growing and the frustration of how would you come up with a theory of strong interaction that allows you to speak of quarks as physical objects. If you read Gell-Mann's paper, he sort of says, well, a little thought would help us know that these are just mathematical entities. In the beginning it was hard to take it seriously in this kind of picture. But fortunately the energy experiments was being increased at SLAC. At Stanford, right, they started to do what we call deep inelastic experiments. They do increase the energy from 1 GeV to 2 GeV to 3 GeV to 5 GeV. In other words, you could go to high energies. So what do I mean by high energies in this case? Right, how do they define it? What should be high energy? It's always, something we have to think what we mean by whatever is big dimension, full number. In this case, obviously, is equivalent that energy is much better, much bigger than the baryon mass, than proton neutron masses, which somehow is the scale where the strong interactions are surely strong. At energies of GeV or below, you won't even talk of quarks. We talk of pions, we talk of protons, we talk of neutrons, and so on. So this is much bigger than, say, M baryon. You could do this experiment. And in spite of the history that would repeat itself, we will find out that molecules are found of atoms, and atoms are found out of nucleus, and basically, electrons fire orbiting around. The picture that people had in mind of the proton was some kind of jelly picture full of this stuff, sort of soft jelly. So if you scatter a hard electron, you would never expect to behave as if you scattered, a free particle inside and we could scatter off. It came as a surprise in the 60s that somehow proton behaved as if it was made of free pieces they called partons. Quarks were so up in the air. They didn't even speak of quarks, they would speak of partons, okay? It was mostly Feynman and Bjorken who suggested this picture, which actually to us is just quarks. So in other words, what the experiment, this you talked about, right? Yes. Indicated, was that the proton behaved, neutron, whatever, I can hit it with an electron, I can hit it with a neutrino, that there was one remarkable thing, as the energy is being increased, that worked better and better. That you will get the scattering electron coming here, as if it is hitting a free, and eventually they would check the cross-section, the way it behaved. It behaved as if you're hitting a spin 1/2 particle, quark, and then reflecting the way it would happen in an elastic scattering. So proton looked at high is it was made out of 3 quarks. When I say 3, to a good approximation, okay, you know, these are not extremely precise statements, okay. The interaction seems to matter very little, okay, the agreements were pretty good. Which is naive scattering of 3 partons, okay, I'll call them quarks. And this became the puzzle of the day. How do you reconcile the strong interaction that binds this guy with something which is weak? And these energies, apparently the strong interaction doesn't exist at all. Now what in the world is going on? Okay. So strong interactions become weak as the energies increase. Why? Did you actually compute some of this? Did you do any homework on this?
We did some running coupling of DFT.
I mean the deep inelastic thing, did you talk about it in some detail? You didn't. Okay, we can think whether we could. Well, this is what should belong to the homological aspect of. So in the moment you are saying these are just words, right? Okay, you will take my word for that. You had these experiments also I can measure. You could look at E plus E minus at high energy. You know, if I think that the quarks are free, I can compute E plus E minus going into QQ bar the way I would compute this going into mu bar. Right, using QED with the appropriate charge substitution. You agree, and the color. Okay, this would be another way of saying color. And it turned out when you compute this, again the hadrons that you produce, it was agreeing with as if you were hitting, as if you were having a point-like scattering with a cross-section growing as 1 plus cosine squared theta. This is the behavior that you get in QED when you calculate E plus E minus going to E plus E minus or E plus E minus. Okay. Notice this interesting dependence 1 plus cosine squared theta. This is the thing that tells you that the interaction is what we call vector-like. You know what we mean by vector-like. Photon has a vector-like interaction. E bar, gamma mu E, it couples to a vector. Not a combination of vector and axial vector, not with a chiral. Okay, and I can just remind you from what you've been doing that this is what you would expect without doing a calculation. You and I know if I go to high energy, this is basically a massless particle, right? So when E plus E minus has been scattered, E plus, let's say E plus going here, E minus going this way, where will the spin, this is sorry, imagine that the theory was chiral, say left. In the left theory, the electron would have helicity minus a half. A left-handed electron, you agree? This would have the, so I would get spin 1, or actually J equal 1 along the z-axis. Okay. And I scatter the guy, they go in the theta direction. Now what will happen, can I have a situation in which I get at the end, whatever that is, let's speak of quarks. Let's imagine I'm producing massless, again massless particle. These states in the end, can we have a particle, whatever particle I'm producing, can the particle go this way? And antiparticle this way? In other words, can theta be 180 degrees?
No.
Why? Because the spin would be in this direction, and I would have the violation of angular momentum. Remember, this is just the thing that will be analog of what we had in the WDK when we polarize it. See, this is a beautiful thing that we said in colliders, these things are polarized. We have fast-moving particles that have well-defined chiralities. So remember, you would get this famous 1 plus cosine theta squared dependence that you had when you looked at WDK. You get the same dependence in a chiral left-handed theory. If it was right-handed, well, it would just be opposite sign. So in the left you will get this, in the right you will get this. So brief reminder, and in the theory is left-right symmetric, you will get the sum of the two. So if the theory is left plus right, like electromagnetic, you would get 1 plus cosine squared theta. So this is the way when you have a new gauge boson, this will be one of the ways of knowing whether the interaction is chiral or vector-like. So if I have this dependence, you know, in a vectoral theory that fits very nicely with massless quarks, so the picture that has emerged as the time went on, once again, as if photon was made out of massless quarks, basically, and free. Another interesting puzzle. It's a huge mass proton, right? Of thousands electron massive, and it's made out of this massless free particle, okay? And the answer is, as Vasif says, the coupling constants run. Okay. So this you're taking my word for that. I may come back and say more, okay? This is what you're discussing with Alex, but you didn't compute. Now, why would you expect the couplings to run? Or in other words, to change with energy?
Maybe that's the question that we always make.
Running. Why we expect that? Even before computing anything, okay? What is sort of physical picture behind it? Let's go back to QED and think why we would expect that. Changing the energy is sort of like changing the distance, right? If I go to very high energies, I'm going closer and closer to the object itself. I'm in a short distance. Right, okay, so you know that. So if I have a typical thing, you know, the textbook example is always if I have a negative charge sitting here, and what happens in a quantum theory is not just this particle, but through the virtual photons that surround this guy, I will have virtual quark electron-positron pairs, so that the plus guy will be attracted to be closer to this guy. I will get something like this if I draw it, and maybe something like this, and so on in this. So if you and I are very far, if you're watching from here, we are not seeing much of this charge. We are getting screened by these charges. To see this charge, I have to go all the way, you know, I have to go as close as possible. So when I go to short distance, I get more charge, bigger coupling. That's basically what it means. Charge is measuring the strength of the coupling.
I don't know, but the charge is not, I mean, not the same. It's not like, because plus minus it cancels.
Yeah, sure.
So,
but in order to see this negative charge, I have to be here. From here, you know, because of the distance, what I see is depending on the distance, right? The impact of the field, the impact of the charge that you feel when you are very far from it gets smaller and smaller. So I'm going to see more the things that are here than the things that were here, and these things are canceling. I'm seeing less impact of this charge when I'm very far.
okay.
Of course the charge is there, but I'm not seeing it, okay, as Galal said, or Vasi, it's being screened by these guys. This is sort of an intuitive way of seeing it. If I want to see the full charge, I want to really come all the way here, as close as possible, so that I'm not already here, I don't see the full charge. I tend to see what is closest to me.
Mm-hmm.
And what is closer to me is a combination which is plus minus, so I will just see less.
Okay.
Well, that's, of course, sort of intuitive hand-waving argument. What you do, you sit down and you compute this. And this is something that one would always hope that the field theory course manages to do. But you did. Not to compute the beta function. To compute the running. You did.
Yes.
Oh.
Not for QED.
That QED.
But for QED.
It's good. It's good. It's good. So anyway, so what happened in the calculation in QED confirmed. This is great. They confirmed that I can write like this. The result in maybe a slightly different form, and then we will try to see that 1 over alpha at energy Z2. The change is logarithmic. You may have written it differently. If you go down, you will see that it looks the same way that I'm writing here, where B is the coefficient that tells me the sign of this coefficient, okay? I don't care at the moment. I'm going to write the general formula in a few seconds, okay? The sign of B tells me what is going on. If B would be positive, then the coupling would. 1 over alpha would grow. Sorry, here, E2. Well, anyway, logarithm is, but let's take E2. Logarithm will change the sign bigger than in 1. If B is 0, then alpha becomes smaller. If B is negative, alpha becomes bigger. And this is what you find out, which you found out in your field theory class, that B is negative. In QED, B is negative. Written in the way I've written, okay. But now, it's a question of how you can, of convention of B. But this is a conventional convention. And you can imagine that, there was this strong intuition that this screening, would somehow, you get used to something, and the screening kind of fits nicely with the thing that what you're getting, the charge is getting. As you're going to higher and higher energy, it's getting bigger. That means when I go into shorter distances, I see more and more charge. Well, that fits of the screening. So there was a strong prejudice that field theory had to generically behave like that. And people started to look at other examples. They computed Yukawas, it took some time. It was Tony Z in the late 60s. And again, the sign was the same as in QED. And finally, in 1971, there was a bombshell by Politzer, Wilczek and Gross, independently computed the behavior of a coupling constant in a non-abelian, which is more general than the abelian cases you've done before. And they found the following. Let me write the formula. This is a generic formula in a theory in which there are gauge bosons. So it has a coefficient 11 over 3rd. Let me define it in a second. T gauge bosons minus 2/3. Notice the signs, T fermions minus 1/3 T scalar. Okay, in order to know the diagrams you have been looking would be diagrams in QED, would be this diagram in which the fermions contribute to the polarization terms of the photons, which has to do with the normalization of charge and so on and so forth. And this is the famous sign of QED, which I normalized in the following manner. Here, let me just tell you that T here in this formula, in general, delta AB is trace of TA, TB generators of your gauge group. This is for your gauge group G, which has generators TA. As usual. Scalars contribute also. The factor is smaller. This is this experience of sort of goes nicely with the screening. Okay, once again, you get the negative side. When I write these 2/3, this is, by fermion, I mean, so let me be precise, a chiral fermion. That means if your theory, if you have a left-handed electron and a right-handed electron, there should be a factor of 2. Each contributes. Sorry, depending on the representation, okay, left and right may be different. In the standard model, okay, SU2. Sorry, you should include them with their proper quantum numbers. Okay, so for example, in QED here you would have charges, would be the corresponding values of the trace of the generator. The generator is just charge, and the trace is summing the charges, okay. And this summarizes, this formula summarizes the formula here. That the particles that you include here in B are the particles whose mass of any particle that you include in coefficient B is much less, is less, sorry, actually works pretty good with this sharp, than E2. Particles that are heavier than the scale to which you're running basically decouple. Okay. And it's a bit naive to expect that they will decouple sort of sharply, but it works pretty well. Okay. We'll try to comment on that as it comes. I just want you to accept this. Since you looked at it in QED, this can be generalized, and the way it works is here. Sorry, n of particle P that contributes to the B coefficient, okay, so that contributes to the running. Okay, so if you and I want to do running between, I don't know, say 2 GeV and 5 GeV, imagine that E1 is 2 GeV and E2 is 5 GeV. Who would I include here? Who will be in the coefficient? The particle, once again, whose mass is
between 2 and 5.
right. It should be, or even below E1, even so much better. No, as long as it's less than E2.
E2 is less than 5.
So, well, anyway, if I'm below 5 GeV, but I'm well, okay, it's not so important because I will include the particles. So, for example, should I include the electron? Yes, it runs. It is lighter than 5 GeV, and muon, yes, and strange quark, yes. And down quark, and up quark, and charm quark is less than 2 GeV. And tau is just about there. But shall I include the bottom quark? No, it's about 5 GeV, okay, that's that's dangerous. No top quark, no W boson, no Z boson, okay. Now increase the energy. So E2 now is 10 GeV. Oh, I say, let me add the B. That way is less than 10 GeV. But do I put a W? No. This is how you issue this formula. But notice this miracle. Two things, that there is an opposite sign. The naive screening thing has to be abandoned when it comes to the gauge boson. The self-interaction of gauge bosons, the fact that they carry charges changes picture completely. We could think like that because photon didn't have charge. We didn't have to worry about the photon that can contribute to the whole picture. Okay. You can't apply the simple intuition. You know. These guys carry charge if you wish, the gauge bosons. And not only that they give you the opposite sign, but they get a much bigger coefficient. So they like to dominate. So in QCD, and you can imagine that then, of course, the people that noticed that immediately said, and the people that were around them when they said that, and people that heard, they said, well, let's then gauge QCD. Let's gauge SU3. The QCD, the theory of strong interaction, obviously, it's custom-made, custom-fit, sorry, tailor-made, as we say, to be a non-abelian gauge theory. Why? At low energies, it should be strong. At this picture, the high energy should be weak. So here was the answer. It was there always from the first moment. It turned out, as usual, that the person who had the idea originally was Nambu, before any of this was known in 1966. This is 1971. But already in 66, numbers suggest that we should gauge QCD in order to have the dynamics, to have the messengers, which is anyways the picture that you and I love, to have messengers be responsible for the forces. So the way photon is responsible for electromagnetic interaction, the gauge bosons of the color should be responsible for the strong interaction. So what we have to learn is how to write this theory. Well, you are there almost basically. And then somehow I would have to teach you. I'm not going to derive that. Next year, for those of you that stay here in many of field theory courses, I find it mind-boggling, you know. It seems sort of that you were part of history for you and the drama. And this, you know, these guys got Nobel Prize. Is an exercise in the field theory course at CISA. It's done now by graduate students. And probably in many other schools. Usually, it's simplifying, you know, people learn techniques which are simpler. So I won't say anything how you would compute that, of course. But even if it can be done, you know, in a graduate course, it's a highly non-trivial calculation. So I want you to stare at it and I want you to accept it, so that you can talk of implications which will be profound. You will see I will then use it to talk of grand unification. And I want to justify SU3 color. Okay, we knew that it had to be SU3, we knew that there was color. Now we are just going to gauge it because of this. Meanwhile, let me ask you, do you know how you would compute this? What is this gauge boson? Which representation of the group they are? And I think that we do that for SUN, right? That would be nice, okay? Not just because tomorrow maybe someone says, why don't you guys look at SU5, say, or whatever you like to look at.
No question.
So yes, please. Oh, I can't erase this.
In this formula for B, should you include also things like fatigue of ghost or ghost
Yes.
bosons?
Yes, you have, yes. You will work in normalizable gauge, so you work in the, with all the fields, you know, these are virtual effects. These are, we're talking about the loop effects. As usually, you would include all the particles. So I have here in the Bible, or maybe before even we write the theory in detail. Sorry, Julian.
But if you have to include the ghost bosons, if you're working with a renormalizable gauge,
Yes.
they don't have a definite mass, no?
Oh,
how would you know that their mass is less than E2 to include them?
The formula works. This is the formula for massless case, if you wish. The thing we are doing that you can include only the particles which are massless at that scale. There is no mass dependence. Sorry, so I should be careful. You should include the Goldstone balls, but you don't have to worry the goals. You don't have to worry the Goldstone balls when you compute it for the massless case. The running is the guy that runs has no mass, if you wish, in the region of running. Thank you. What I said was not correct. You have to prove decoupling. What you have to prove that this naive thing, of course, also this is just one loop and it's a bit naive, this logarithmic simple formula. You have to prove that you can ignore the mass all the way, you know, which sounds a little crazy because it's the particle that is heavier decouples. Okay, that you have to prove. So that you can determine the particle that this is basically massless. In other words, this is the behavior of the coupling constant, which actually, the actual calculation is more complicated. This summarizes to a good precision the way it works. Actually, the particles that are running there are basically massless. That's crucial. Otherwise, it was a good question. Let's try to see if we could apply this formula before we speak more of the dynamics. Okay, when you give you a formula, it would be nice, then we know how to use it. So let's see, for example, suppose that I'm in this, I'm looking at the SU2 cross U1, SU2 of the standard model. You know, I would have fermions like this. Let's see if you and I can apply it. I want to look at the fermions. So let me run in the region when I have massless fermions. Okay. I mean the energy is below W. So how would I compute here TF? I want to compute TF for the standard model U1 representation. Okay. Help me. This is it. For example, will ER contribute to the running of SU2? No, because T here, right, is 0 for these guys. That's the definition of being a singlet. What is T left? Is sigma over 2. So we know that. So what is T? Well, it's a half. That's how we normalize. Doublet has a half. Okay, this is a convention because in SU2F is epsilon, and that fixes the convention of the normalization. Okay, we keep in any group. So TF is for this multiplet. Okay, TF of mu E is, and I can just do this.
What is the F, sorry?
T is this.
What
This
is
is
that?
T. F stands for fermion.
What, that fancy T is the same T?
Oh, you mean the way I wrote?
Ah,
Yeah, I just wanted to sort of emphasize this is generic T.
and you have 3 indices there?
3 delta AB is trace.
Ah, okay, okay.
Sorry.
Sorry, I didn't see anything. Okay,
The usual normalization. I'm sorry.
Yeah.
In my head, I think it was not clear.
okay.
So TF, okay, it's good.
Okay.
Mu E will contribute, which I said, a half. UD will contribute, 1/2. 1/2. Second time. 1/2. Third time. Walks carry color.
3.
If you forget color, you know, that's the whole thing. Times 3. This is, I think, 2, to a good approximation. So T fermion in the SU2 of the standard model is 2, and then if there are n generations, I would just multiply times n generations. You agree? This would be T fermions of my SU2 standard model. Let's compute T3. Sorry, T, okay. Let's do SU3. I want to make sure that you know how to use this. Together. T3 now. Okay. I just computed it here. So I could write for SU2, for SU3, for the color. Okay. Mu E, how much do they contribute? 0, they are leptons. ER, 0. UR,
Does it transform the same way? Because
it's a triplet of color.
color.
Now notice, now I'm in SU3, so you may be asking, okay, this is a normalization. So we just said that T, okay, I've reminded you here, Okay, some of the elementary group theory. T for the fundamental representation in SU2, for the fundamental, is a half. That's a Pauli matrix. But this is true of any SUN group, because inside SUN there is SU2, so you normalize the same way, and we did it in SU3, we took the Gell-Mann matrices, we said a half. So this is true of SUN. This is, it all starts free. From there I can build everything. So you are, once again, sorry that I should just write it down and not bug you and let you be in peace, but I want us to, you know, once if you say, it's a half, it's a triplet of SU2, so it's a half. And DR?
Everything's half, right?
And UL?
So should be 2.
And DL? Here we are. So this is 2. Notice it's interesting, we got the same number. It's kind of amusing, okay? We could maybe one day try to understand the times number of generations. So it's very easy to do the formula. Oh, by the way, if I'm now in the SU2, if I wanted to calculate T scalar in SU2, then of course I will just, SU2, I mean the minimal model, I have a doublet. What will be scalar? It's a doublet. I don't know why this is confusing. The T itself is just a property of the group theory. It has nothing to do with the spin. The spin is here. Fermion has a different coefficient from a scalar, but they all have the same dependence when they have the same quantum numbers. Okay, so this will be a half. The scalar would be a half because there is just one doublet. If I tell you that there are 3 doublets, if they find 2 more Higgs doublets, then the coefficient would be 3 half. Okay, I would just count it, okay, if I go to very high energies. So of course this is if when I go to very high energies, SU3. Now, how would I compute the gauge boson contribution? Let me now go to very high energies, okay, and let me now ask you, which I asked Florian before, to accept that when you run your massless, you can be treated as massless particle, therefore I can compute the running of gauge bosons in the unbroken non-abelian gauge here. But tell me, how would you, okay, at least SU2. We'll be systematic in a minute, we'll write down the formula. So let's do the joint now, which is gauge boson. By the way, once you learn a joint, you can apply it. For example, someone tells you, how do the a joint representation in SU5 run? Well, you give them the formula immediately. Every adjoint runs the same way. As far as T goes, gauge boson has a coefficient 2/3. Fermion would have 2/3 if it existed, and the scalar would have a third. So SU2. Let's start with SU2, and then we generate SU2. What will be T for?
3.
For SU2.
1/2.
You just said that's a fundamental representation. How can they be the same? Now, gauge bosons, there are 3 of them. How can they? What is an adjoint of SU2? It is what we call a vector of SU3. What are the it's a spin 1 if you wish, SO3, or spin 1 if you wish. So what are the eigenvalues? How would T look like?
1,
0 minus 1.
Yes.
So what would be T for the SU2 adjoint? This is T. It's a trace.
So 2.
You take any matrix you like. Take always Cartan. Take the diagonal one. That's the fastest way. So it's
2.
So that's not so hard. SU2. How would I do SU3? It's not easy, you know, 8 times 8 matrix is okay, I hate that. Well, it has to do with those FABCs. We could maybe try to, but I want us to think a little bit. So I'm not being systematic, I want us to, I would like you to appreciate sort of doing this group theory with your fingers, if you wish. Not SU3 adjoint. What is an adjoint of SU3? It's an octet. Well, look, you and I know SU2. Remember I told you that if you know SU2, you will know everything? I kept telling you, so learn SU2 and you will know anything, okay? You have to think a little bit. So if I have an octet of SU3, and I don't know how to work with SU3, I'm going to decompose it in SU2. So how do I decompose the octet in? What do I get?
2 top plus 1, 2, 3.
Yes. 1 triplet. So this is SU3 octet. Okay. How do I decompose the octet? How does the octet of meson look like? What do I have? There are 3 pions. That's a 3. So in SU2 there is a triplet.
1 triplet, 2 doublets.
Just think of pions.
2 doublets.
2 doublets. Thank you. Doublet and anti-doublet. Well, 2 doublets. So there is 2 plus 2.
1 singlet.
So let's say this will be pions. 5. This will be kaon. This will be k bar. K plus k0 doublet. And the singlet. Great. And notice this orthogonal representation, they have nothing to do with each other. They live in the different spaces. So if I'm to calculate T of 8, which is a trace of this thing, they are going to add up. I could write here 2 bar, but remember, anti-doublet is same as doublet, phi tilde. They transform basically the same way. SU2 is pseudo-real. It's always Pauli matrix. What is this? This is 2. This is. Try to pay attention to this. You won't easily find this in books, okay? Often it's done very formally, okay? Now, if you like formal group theory, you can do this more elegantly than me, I'm sure, okay? But I sort of don't have to be smart, or I don't have to know too much. So this is 3 altogether. So in SU2 it was 2, in SU3 it is 3. What's going to happen in SU4? Probably 4, right? Now we should try to generalize. Okay. So I'll come here and we'll summarize this. Let me erase it. Let me use the privilege of the blackboard just to say, well, let me make a bold statement. Let me make a conjecture. Okay. P adjoint of SUN is N. How would we prove it, you and I?
Put it in SU2.
Yeah, but I want to prove it for N. I cannot not do now SU4. That no matter how far I go, right, there is an integer, there is always a bigger integer. So how do I do this? By induction, no? So let's try. Let's try to prove it. Well, we check it for 2 and 3. We already done enough. So let's assume that this is valid for N. And let's compute PA for SUN plus 1. Now, what is the adjoint? How did I get the adjoint? Okay, this is the only thing, one more thing we have to know. How did I get the adjoint of SU2? Adjoint now is a better language than a vector. Okay, because in SU2 it was a vector, here it is not a vector, okay. What was the adjoint, just to remind us? Okay, I can erase this number just to remind us what adjoint is. Adjoint representation, A, I can call it U, AU dagger transforms, right?
One of the same dimensions of
And remember how, for example, in the gauge boson case, How you get it, for example, on fermions, you get it from covariant derivative. Remember, so you get interaction which is of this type. This is why it transforms like this. So in other words, a joint is equivalent to n times n bar. This is how you got it. How did you get the triplet? You took 2 times 2 bar, spin times anti-spin. How did you get a joint in SU3? Well, 3 times 3 bar, and you make it traceless. The only thing, of course, it's traceless because remember what we said, that under this operation trace is invariant, therefore I irreducible representation trace A sub 0. So this is the this is the adjoint. So in other words, in SUN, a joint was equivalent a traceless part of n times n bar. What is it in SUN plus 1? Well, the adjoint of n plus 1 is n plus 1 bar, you agree? Times n plus 1. What is this? This is n plus n bar plus n times 1 is n times 1 n bar, and then there is 1. Or maybe there is no 1 because it's traceless. Let me think. Or maybe there is. Who cares? It doesn't matter. It doesn't contribute. I don't have to be careful even here. Or you can count it. So that means the adjoint, that's what you actually, this is what you learned in SU3. You know the adjoint of, it's an adjoint of SU2 plus a vector plus an anti-vector plus 1. Obviously, n plus 1 is the same thing. It's always there. It's just for the transformation property. Okay, this is not plus n times n bar. This is an. This is a fundamental of fundamental bar. So what is this then? The thing is the T of an plus T of n plus T of n bar. T of n we assumed by, this is how we decided to prove it, we are using induction, so T of n is n, we said. This is a fundamental, n-dimensional fundamental, which has conventionally, this is how it all started, half. And n bar has a half, it's the same representation, just n type. And this has 0, so I get n plus 1 QED. So actually we managed to compute. Jesus. There must be a more elegant way of computing it, or a more mathematical way of computing it. Sorry, you know, I never want to look it up. Well, maybe you should look it up and tell me about it. Okay, I would appreciate what you said, especially those of you that maybe like fancy group theory. You can see the way I work, that I don't like fancy group theory. I tried. There was a time when I got interested in extra dimensional and thinking diagrams and all of that. Most of it evaporated. I don't live with it. And you know, you remember what you do, not what you learn. What you learn, you forget. I don't know why, but it seems to be a fact of life, right? That eventually we tend to forget if we don't somehow do it ourselves. So even if you don't understand fully how I would derive this formula, but you know, if I can treat it as a master gauge bosons, then I can see from Julian's question and from the way you told me that you did in the field theory course, it would be just a more complicated calculation than what you did with SAFE. Right? You would do basically the same thing. And you would end up with this magical thing that would turn out to be positive. They even, Wilczek and Gross, you know, they say themselves they had a wrong sign for a while, which they had to check it. You know, they had a negative sign, and you think that it should be negative, so you're even happy with that, okay, but then you go on checking, and it makes all the difference, okay. So if we can, you know, if you understand, and I want to pose it that this derivation, we can apply it now. We can compute the, you know, running of the standard model. And let's check asymptotic freedom, number one. We have to make sure that the theory of strong interactions is asymptotically free. And then we have to think what could spoil that in the future, in principle. But let me know before I start erasing. Let's try to keep this. We'll now generalize it. Okay, it's actually when I say you should know SU2, actually one should know SU3 also. Although knowing SU3 is knowing SU2 well, but once you know that too, it helps you to generalize. By the way, I know how to run SU5. I can now take any grand unified theory and see what happens when I even at such high energies, okay. Because it's an adjoint of n, so n is 5. Okay, I erase this. And let me read this formula. Let's now look first at, let us imagine that QCD is therefore SU3 gauge C. By the way, this is something that we don't have to worry about how to compute. This is supposed to be unbroken, okay? We have strong prejudice that gluons are massless. The ideas of confinement that I will talk at the moment. You see the beauty of this simple formula is surely valid for massless particles. Would tell me that, naively at least, of course it will break down. If I go to higher energies, the quarks will be freer and freer if they are bound by SU3 gauge bosons, or SUN gauge boson, SU3 in particular. If I go to smaller and smaller energies, right, I will have the opposite effect, and the coupling constant eventually will blow up. Of course, this will then not be valid, so I have to find a better way to prove it. But there is a strong indication that I may marry the asymptotic freedom, we call it, of high energy physics to the infrared slavery, we call it, the confinement of quarks. This strange fact that we never see free quarks. So how would the QCD Lagrangian look like? Well, just like all of the others, let me just, it is often written, because there are gluons inside with G and not with F, there will be index A, and A will go from 1 to 8. A bit different. And there are quarks only that couple to gluons. And for each quark, I will just write down the usual, and I will sum over my quarks, right? Remember, this notation is generic. As long as I know a few things, that d mu is d mu minus IG TA G mu A. These are the gluons. There are 8 gluons. And this would be lambda A over 2. And I write only the quark. If there is a lepton, you would say the lambda on the lepton is 0. The lepton is a singlet of that. And then quarks have masses, and you could write them Q bar Q. If you just think of strong interactions, at this moment I don't have to worry about the Higgs, for example. Higgs doesn't have strong interactions. For me, when I speak of interactions, it's Lagrangian. You see how simple it is. And this is somehow something I find mind-boggling, and I wonder whether this can be, like I said, I always feel when people come up with very complicated, complex, baroque explication of simple phenomena, that somehow it won't be true. The thing, of course, it doesn't mean that this is easy. This is extremely profound and deep theory, because we are still trying to compute with the theory when we go to low energies. But it's simple, based on a simple principle, simple to sort of illustrate, simple to show. Maybe hard to work out. just like gravity is, but at least conceptually. There is a beauty in that, and depth. So you see what the gluons do. Inside these lambda A's, there are cartons, which is lambda 3 and lambda 8. The cartan guys are sort of innocuous. They don't do anything. Sort of, right? They are diagonal, so they don't, just like photon. Photon doesn't do much to you. You sort of, you scatter, but you don't change your nature, right? If you're an electron, you stay an electron. So the cartan guys are like photons, you agree? Red quark will stay red quark. So notice when I say that there's a quark here, I mean that the quark has 3 colors. So Q red, Q yellow, say Q blue. I can write it as a column or a row, it doesn't matter. I would normally write it as a column. So these two guys, what they will do, they will leave red, red, yellow, yellow, and blue, blue. The off-diagonal guys do the same thing that the W does for the flavor. W takes neutrino, makes it become an electron. And these guys like to take a red quark and make it a blue quark, and then a yellow quark, and then going back, and so on. Okay. So there is a drama there. If you carry color, you and I don't carry color, so we know nothing about it. Let me finish the lecture on this sort of mathematical aspect on how to compute, and then we come back and think more about the physics. Think a little bit about the confinement, how could we really unify these two pictures. Think of how we often used to imagine, you know, pions being mediators of the strong force on the nuclear level. We'll try to sort of give you an idea of that. But let's compute, in order for us to sort of become experts on this, let's compute this for the standard model. Let's go to high energies. Now, the nice thing is about QCD, the high energies here is just defined in the energy compared to the quark mass. Right? Gluons are massless. No mass term here. Notice. So, okay, I want to compute B3, which is B of the SU3 gauge theory, or SU3 color, which is B of QCD. Let's start with that complete formula. So what will it be? It will be 11/3 times 3 minus, we computed already the fermions. Remember, we got 2 times number of generations. What about scalars?
There's no
0.
There's no scalar.
As far as we know.
Yes, as far as
Ignorance can be a bliss, right? Life is simpler. But kidding aside, there are no color-like scalars. Okay, they may appear one day. We'll worry about that in the future. Presumably, they should be confined. I don't know. So what is this? Oh, I missed something. 2/3. This was just T. Thank you. 2/3. So this is what would be a smart way of writing it. I could write it as 33 minus 4 number of generations divided by 3. Am I right? Yes. So notice, as long as number of generations is less than 9, the theorem is asymptotically free. This is kind of neat if you were to go to very high energies. And of course, at the energies that they have been looking when this was being established, at 10 GeV, say, the number of generations was even smaller. There was no top quark to do the running, okay? But even if I go now to 100 GeV at LHC, for example, this formula applies beautifully with number of 3 generations, okay, that we have found. No other generation has been observed. So this becomes, what is this? 12
Yes.
7.
Mm,
It's a nice integer number. So this is sort of the picture. And you notice that the picture depends on how big your alpha is. The bigger alpha is, the more you run. Okay? When alpha is very small, then these numbers are huge. And therefore the running is irrelevant. But when alphas are very big, then these numbers are not small. And then of course the running is important. So the QCD, you know, let me try to emphasize it, okay? It runs a lot, and then it starts running less and 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 less. And to give you an idea, the thing that has been measured is alpha strong. Today we notice alpha strong at MZ. Okay, at around 100 GeV, it is usually found in MZ, where you have the energy set by the Z mass.
Yeah.
And you can measure the effect of alpha strong in the, you know, when the Z decays in QQ bar, actually you should introduce corrections due to QCD. You know, everything that we do, we now don't treat quarks as free. Okay, this was the beginning that led to the SU3 gauge theory. Meanwhile, there has been, you know, the industry of perturbative improvements in which you treat the QCD interactions and you see actually the correction to the freedom. Quarks behave not as if they are free, they behave as if they are coupled precisely the way QCD says. And why does it work? Why you can do perturbation theory? Because this is 1/10 roughly. So you see, this is a great lack of asymptotic freedom. When you do collider physics, you are almost in the same regime. Just to remind you, at the same scale, alpha V is 1/30 left. So this is alpha, and this is energy. And if I am, you know, at 100 GeV, this is roughly 1/10. And this, by the way, is the B3, or often written as B strong, or BC for color, for the standard model. If I go to the LSE energy, this is precisely what the standard model should give me. Okay, I'm above now the masses. Okay, I can safely work as if even the top quark is massless with this particular formula. So that was SU3, B3. B2, let's just compute B2, which means now I want to apply to very high energies to be sure. Okay, but I will still talk of MZ, but it will be better maybe to speak of LHC when W is really massless, okay. So when I compute E2, I will pretend that W is massless by this sharp decoupling. So what would be B2? So SU2. B2 is 11/3 times 2 minus, we got the same coefficient. So this is kind of neat. And then there was -1/3, remember, for the Higgs, times 1/2 we got. Higgs is a doublet. So if you believe that there are more, you know, or say, you work in a 2 Higgs doublet model, you are sure they're going to find it. Okay, put here the number of Higgs doublets if you like. The impact will be very small. Notice that it runs much less than gauge bosons, fortunately. This is very nice because this is a sector that we really don't know very well. We could have surprises here, but the impact will be very small. I'll tell you why I'm saying this in a second. So this is 22 minus 12 So this is 22. I will apply to 3 generations. I get 22 minus 12 divided by 3. Did I do correct? Yeah. Minus
Minus 1/6.
minus 1/6. Okay. It's sort of ugly. So let's imagine that there are 2 Higgs doublets. it makes no difference, basically. No, just sort of that you get a feel. Let's imagine that there are 2 Higgs doublets. Okay. In the left-right symmetric theory, there will be 2. You and I may like left-right. So there will be minus 1 here. And that will be altogether 9/3. Am I right? So you see, the interesting thing is that what matters is a relative coefficient, okay? Now, this is also, it turns out, asymptotically free in the Sander model, okay? It's not a big deal. We don't care so much. The weak interaction is weak anyway. Who cares? Even if the coupling were slowly become a little bigger, we wouldn't worry too much. But so much the better. So how it would look like? Well, it would start here. It will be smaller. It will be much smaller, right? But it would also fall down slower. You agree that eventually they would meet. Their slopes are different. So they're going to meet. They're not going to be parallel.
Yes.
I can compute where they meet. Or you can compute where they meet. We could maybe put in the number. But the only way to put the number in, remember, is to the homework. And then what is very interesting, they meet around 10 to the 15 or so GeV. It's kind of amusing. So you can imagine the excitement in 1974. Okay, we just mentioned this and we stopped. When Georgia and Glesher suggested that maybe there is a grand unified theory of SU5. Well, grand unification means that what the word says, that the couplings unify, everything unifies. So that means that if I go to high energies, but I can go and check that. So 6 months after they said this, 1974, George I, the same George I, Quinn and Weinberg, they actually computed the running. Now you have to run U1. Now you agree that if U1 runs, there will be no reason that you should hit. You know, it's a miracle because we are running orders and orders of magnitude. And what happened now in 1974 was a bombshell. They found out that actually even the third coupling unifies at the same point. So the whole world exploded with enthusiasm for grand unification. Look, it all fits together. They would like to unify.
And that's only in supersymmetry.
Well, okay, it's not now, it's getting late. I just need a few more minutes if you don't mind, okay, to finish the lecture because we are going to have the whole week off. I need this little time. We'll have to make up a lecture on Wednesday, as I said. So you don't mind a few more minutes, in spite of being hungry, just to finish here. Well, they got it to unify. And everybody got excited, obviously. As Moritz Goldhaber said nicely, everybody rushed underground. The whole world decided to look for new physics because if they unify, that means that there is new physics here. According to grand unification, there will be a new gauge boson. But you and I already saw what the gauge boson would do. It was easy to see that, okay? Wait, let me remind you. What would the gauge boson do? I'll write this next time when we come back if you see these things. What does grand unification mean? That I put quarks. And you and I learned how to do that. I would put a lepton doublet here, this is SU2, I would put the we decided the charge is sum to zero, it's traceless, so this was anti-up quark in 3 colors. So here lives W boson, right? This is what W likes to do for its living. It takes a neutrino, makes it an electron. Here lives a gluon. Takes red into red, yellow, blue. That means there will be new gauge boson, X guy. And what it likes to do, this crazy guy, likes to take a quark, make it an electron. It's a very funny gauge boson. Its gauge boson carries charge. How much charge does it carry? Well, if it takes, okay, help me here. If it takes a down quark to a neutrino, how much charge will it carry? 1/3. Third to zero. But if it goes from here to here, it would have a charge of 4/3.
Yes.
Well, it's not surprising because it would be a doublet of SU2. You see, it would take singlet, this is a singlet into a doublet, and the difference of charges in a doublet, in other words, there will be 2 gauge bosons X and Y, with charges at 4/3 and 1/3. Or minus 1/3 and 4/3, okay? The difference in a doublet must be 1 charges. Remember, it was always neutrino, 0, electron minus 1, up quark 2/3, and so on. This is just T3. Q is T3 plus Y over 2. Delta Q is delta T3. Y must be the same, which is plus 1 because T3 is sigma 3 over 2. And this gauge boson, it is easy to see what it does. It makes proton decay. You may have forgotten, let's try to do this. Let's see if with hunger and restlessness we can do it. We can do it. How would I compute the proton lifetime or decay rate? I mean, what would really happen? Let's try to see. U and D. D, according to this guy, DC can become E. That means that D can become EC. Same thing. And what is going out? This is plus, so there is some guy with charge, what, minus 4/3, am I right? So it will be X bar going down. And therefore, if it has minus 2/3, I could have an up quark here, which has 2/3, and have a charge going out minus 2/3. I want here 4/3 to enter. This will be UC. Am I right?
Minus 2/3. Then you have the extra U and then you bar, that's fine.
UC is minus 2/3 going out. It's like 2/3 going in.
Yes, minus 2/3.
So this is good. Or wrong?
The other was
I have minus 4/3 entering here, 2/3 entering here, and
minus 2/3, yes.
and I need another 2/3 to enter here.
Yeah.
That's minus 2/3 going out.
Yes.
Okay. And then I can have here another up quark. This is good. A spectator quark. This guy is just watching. Becoming U. This is pi. So really what we have is the usual 3-body decay of the... let's stop here in 1, 2, 3 minutes. So what will the gamma rate for P decay? Is 1 over mx to the 4th, g to the 4th, and then m proton to the 5th power. Yeah, you just did it with 192 pi cube.
Yes.
So gamma proton over gamma muon, G force would cancel, more or less, okay, there may be some running which is logarithm. Then I will get here mw over mx to the fourth times m proton over m muon to the fifth power. I don't even have to worry about the coefficient. Let me just say this. It's one of those moments when I'm lucky that okay. What do I get? That tau p is tau mu times mx over mw to the fourth. And this is 10 to the minus, this is mu over mp, which is, there will be 10 to the minus 5. mu over mp, 10 to the minus 5. How much is t mu?
10 to minus 6.
10 to the minus 6 times 10 to the minus 5, 10 to the minus 11 seconds times mx over mw to the fourth. This had to be bigger than 10 to the 30 years, which was the limit at that era. So they knew immediately when they wrote the theory, Georgia and Glashow, that mx has to be bigger than what? How much is a year? It's about 10 to the 8 seconds, right? It's pi times 10 to the 7, I remember. It's 10 to the 8. So this is 10 to the 38 seconds. Then 10 to the 38 seconds, this is 10 to the minus 11, so that's 10 to the 49 times mw. I don't write 10 to the 49, so why don't we change the limit actually improved very quickly, okay, because people didn't see it. We'll put a nice number there. I need 3 orders of magnitude. So this is going to be 41, no, 33, what do I want? 33 years will be 10 to the, 41 seconds. So this will become 52. Yes. Take this. This is true, by the way. It's even better than this. I just want to, mx would have to be bigger than 10 to the 13 mw, which is 10 to the 15 GeV. That's what you and I know. If there's a new gauge boson that these guys want to suggest, it has to weigh more than the 10 to the 15 GeV. But they found out that the couplings unify 10 to the 15 GeV precise. Actually, they put a smaller number, so they knew they had to be bigger than 10 to the 14 something GeV, okay? I just wanted us to have a nice number, okay? The lifetime was just to give you a feeling. And they found out that the couplings unify at this energy of unification, which is about 10 to the 15 GeV. But the unification, but the new physics is taking place. This is what unification means. There will be now new physics. See, these guys will now, above their mass, they will become massless. I have this decoupling, and the gauge couplings will run as one. That I'll show you in a lecture dedicated to this, okay? But you can imagine the excitement, because now what they said, I now predict the proton lifetime to be about 10 to the 33 years. And people knew that they could reach that. Not only did they reach that limit, today is 10 to the 35 years, okay? The answer to this is the couplings do not unify in the standard model, because then they were measured better. When you measure them better, then I'll try to tell you more after we go back and understand QCD. I just want you to appreciate the importance of running. It allows us, in principle, to make statements about very high energies. Okay. Any last question?
measurements, we know that the couplings don't are the same.
Sorry?
From measurements, do we know that the couplings
Yes, 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 they have been measured better. What happens in the standard model? If you are curious, in the standard model, what happens, the picture can be drawn like this. Of course, it's logarithmic. SU3 and SU2, they meet here. 3 and 2 at the scale of 10 to the 15, roughly. 16. Don't ask me now. It's more, a little bit more. It's more like 10 to the 16, 10 to the 15.5. The U1 coupling is not asymptotically free, obviously, right?
Yes.
The electromagnetic coupling. It turns out that it hits this much earlier, around 10 to the 11 GeV. Okay, I exaggerated here. It wrote it in the standard model. This is because it was measured better. What was measured better was sin squared theta W. Okay, that's like measuring better the couplings of the standard model. You knew the electromagnetic coupling, you didn't know SU2 and so on. Okay, the things changed. This coupling changed, so it ran a little differently. Me, this guy a little later, maybe more like 10 to the 16 GeV. Okay, this number is not so important. This is the picture of. But this is interesting because this we know today. Around 1980, witnessed an excitement of supersymmetry, low energy supersymmetry for various reasons, okay. Now we have a course on supersymmetry. I don't know whether that's justified or not. It's still a speculation. There's no trace of supersymmetry, okay. But anyway. And so people fell in love with supersymmetry. And you can imagine, and then it was Wilczek, Dimopoulos, and Raby suggested immediately that this has to be redone if there is supersymmetry, because there are supersymmetric partners. And did the calculation, which was not too complete. They did it at 1-2 level, and there was a, they ignored the scale, as roughly they were right. And then there were two groups, Einhorn and Jones. And Marciano and myself and in Brookhaven, we did it actually this seriously, 2-loop, detailed unification. And we found out that in supersymmetry they could meet if sin squared theta W was 0.23. At that time, experiment said that this thing was 0.20. This is what you asked me. This was measured wrongly at the time. Well, actually, it was interpolated. To get to this number, people assumed that M top was very light, around 10 GeV. And what we found out that if we suggested that if M top, what we said that if F top would weigh about 200 GeV, we could decrease sin squared W to 0.23. We decided to stick our neck out. I'm proud of this. Whether this is true or not, I'm not as excited as I was for a while, because lo and behold, 10 years later, this was 1981 when we wrote the paper. In 1991, sin squared W was measured at LEP, and it was to be found to be 0.23, as suggested by supersymmetry. So you could say there was something prophetic. 5 years later, top quark was found, and it had a mass of around 200 GeV. So there is much more to it, and therefore when I finish the course, I'll come back to it. And that's neutrino physics, so I don't, whereas this could be true, this is not the only way to have unification. I studied without supersymmetry. I have vested interest, but I believe less than I did. So, anyway. Okay, I should stop. It's getting late. Just want to make sure that there is a last public question. If not, we turn off this. Yes. No, I mean, we do it.
You
No, it's the other one.